Hello, hello. I hope y'all are doing well. So today what we're gonna do, um, just switching pen types here. We're gonna learn about magnetism. Let me get used to this. Maybe that's a little thick. So that's the subject of today's lecture. What we're looking at is we're gonna talk about, well, first, what is magnetism? And also, how do they work? Okay. But after we start doing that, we're going to delve. Once we start doing that, we're going to start talking about more. We're going to start talking more about specific examples. And under that, we'll talk about like the force on objects and between them. So we'll talk a little bit about what magnetism can do in terms of force. So first off, let's talk about what is magnetism. So magnetism has been around for a long time. You know, people discovered rocks as far back as 1000 BC. And no one really knew kind of what it was, okay? So basically, it was discovered in a piece of a naturally occurring mineral known as magnetite. And you must be wondering, well, how does it even like get this name, right? And so this stuff was discovered in Magnesia was the location for it. And so you can kind of see where the name came from, right? But anyway, people would look at this and be like, well, what the heck? What the heck is this random force that we have no idea about, right? You look at this stuff and it's, you know, you have two pieces of rock and suddenly they're either attracted to each other or they're repelled by each other and they're not even touching. And so it's like, what is actually happening? And so even today, like, you know, there's memes on it. It's like, how do magnets work, right? Like, no one really knows. And so even today, it's still like hard to figure out, you know, if you're not taking a physics course, how they even work, right? You have to actively look it up because it's not really obvious. Yeah, so now let's look at, so that's kind of like the history of magnetism, right? But now we want to know like what actually is it. So let's define it. So magnetism, right? If you start with anything, you should define it. Magnetism would be a class of physical phenomena mediated by magnetic fields. So particularly that last bit talking about fields, that's something we've seen before where you can actually, you know, have some objects that are completely separated and this action at a distance is what it's called, can happen, right? And so we saw it with electric fields where charged independently charged objects, not even touching, not even related to each other, would interact with each other from a distance, right? And they did that through the electric field. Turns out magnetism via magnetic fields, okay? So let's look up exactly what a magnetic field looks like. So if you remember with electric fields, right? So for electric fields, what this would look like would you'd have these, how you could end up imagining it, but for a positive object, here let me do it in the center. For a positive object, you would have these fields just radiating outwards, and they would decrease in strength over, r squared, right? It was an inverse square law. And if you placed any other charge object in the middle of this, what would happen would be that it would interact via this field with this guy. And so it would be repelled or attracted depending on its charge. And that's kind of what electric fields look like. So magnetic fields, how they looked is just a little bit different. And what I'm going to do is just give you like a little bar magnet. So here's a north-south, so this is a bar magnet. Okay. And what happens is magnetic fields form these closed loops that go from north-south. Okay. So you must be wondering then, what actually is this? So let's look at similarities to the electric field. So similarities to the E field. Field lines go from north to south. This is analogous to plus minus, right? So this is plus to minus for electric fields, okay? And that's about it. Their differences are kind of more of them. So there's more differences than there are similarities. So differences, what you see is that first of all, they form closed loops. We didn't see this with electric fields. Electric fields, they start on the charge and then they terminate on the, so they start on the surface of the positive charge and they terminate on the surface of the negative charge. They don't actually loop around, right, towards each other. So with these guys, though, they do form closed loops. The other difference is that you need two of them. You need both poles for a magnetic field. I should say experimentally. Theoretically, it's possible that this isn't the case, but everything we've seen for, ever since we've been studying this and been developing research on this, is that there's two, and there's always two. If you take a bar magnet and you divide it in two, what you end up getting is two little bar magnets. Okay, and you can just keep dividing them up, and then you get 4, and then you get 8, 16, 32, right? It just keeps doubling. So poles cannot exist independently. Like charges can, okay? They're not independent at all. You can have a plus charge by itself, positive charge by itself, negative charge by itself, but you cannot isolate a north pole by itself. If there's a North Pole, there's a South Pole somewhere around. That said, theoretically, as I was saying before, it might be possible to discover scrolling is hard. Might be possible to discover a magnetic monopole. Whoops, monopole is what it's called. But like I said, that we haven't really seen that experimentally. Okay, but there's no reason that it's not a thing, right? So there's no, I should say there's no mathematical reason why it can't exist. It's just we haven't experimentally found it. Okay. So now real quick, just a quick little example, because everyone always wonders, like, what about Earth and its poles? So we're told that the Earth has like a North Pole and a South Pole, right? Geographically and magnetically. So if you look at it, I'm going to attempt to draw a little Earth here. There's Florida, South America, there's Europe, and then that's Africa, right? Kind of, I guess. It doesn't look that great. Anyway, so here's the Earth, and this is the North Pole geographically. And this is the South Pole, right? Antarctica's down here. There's Antarctica. Geographically, right? But what actually happens is you have, that kind of looks like a face. It's kind of funny. So what happens is if you put the little magnet in here, what actually looks like is you have the South Pole up here and you have the North Pole down here, and it's tilted. The inclination is like 20-something degrees, I think. I wrote down on my notes 0 degrees to 20 degrees. It's something like that is what this theta is here. That it's off the geographical. And not only that, you have South Pole up by North Pole and North Pole down by South Pole. So as you can see, it's really freaking annoying when you're actually dealing with this stuff. So when you're looking at the North Pole of a magnet, it's actually pointing towards the South Pole, kind of, and then vice versa. And so it's a little bit annoying, kind of how it's kind of a little bit backwards for us, because it's kind of like with circuits. We were dealing with circuits, and it's actually the flow of positive charge that we were actually doing, even though the electrons are the ones that actually flow. It's similar to that. So what actually happens then is, if you have like a magnet, right, with a little needle on it, how come that points to the quote-unquote North Pole? This is a south that's actually pointing. So that will, or it's a, sorry, apologies, it's a North pole in the magnet, and so it basically aligns along the magnetic field lines, which kind of look like this. Basically just a blown up bar magnet is kind of what it looks like. And these magnetic field lines of Earth are actually pretty powerful, and they save us every day from charged particles and charged fields and things like that from striking Earth. It basically shields us from it. If they didn't exist, if we didn't have a magnetic field, life as we know it probably wouldn't exist. So it's very, very important that we have this. So starting off, I was talking, what is magnetism, right? And I haven't really, I defined it. I said, it's a class of physical phenomenon that's mediated by magnetic fields, and then I kind of showed what magnetic fields were. But we still haven't, said about the source of a magnetic field. So what actually causes it in the first place, and the source of magnetism in the first place? So causes a magnetic field. Why does the Earth have one? Why do magnets have them? How come, you can make one, right? So it turns out that what causes it is moving charges or moving charge. This is imperative. This is the sole reason we have a magnetic field. So all of that stuff that we talked about with currents, where we actually are creating circuits and stuff, and there's electrons flowing through them, those generate magnetic fields due to the movement of charge. You move a charge, it generates a magnetic field. Okay, and so so let's talk about the types of moving charge. So types of moving charges, and this is also known as current, right? The flow of charge per time, right? The movement of charge per time. That is a current. So we've got a few of them. We've got the first one is just, if you're looking at it, right, because you've got charges literally everywhere, so you've got electrons, and they're orbiting an atom. So they're actual, since they're moving and they're orbiting, they're generating a magnetic field. And you can kind of see then why modeling this stuff, anything more than just hydrogen, is extremely complicated, because you've got these individual electrons and multiple, sometimes hundreds, right? Depending on the atom that we're talking about, you can have tons of electrons, and they're orbiting all, right? They're all orbiting, and so they're all generating their own magnetic fields, which are all interacting with them, and then those magnetic fields interact with the charges, and you can see it's extremely complicated. But that is a type. Another one is this thing called spin. And so what this is an intrinsic property, an intrinsic form of angular momentum. So if you look at it, this is, a really garbage model of an electron because it's a particle, it's a point particle, it doesn't actually take up volume, but what it is they're like kind of, you can think of them as just spinning in place. So you take an electron and it has this property spin, which you can think of it as spinning, but it's not technically spinning because it's a particle, and they take up no volume, but what it does is it's basically got the effect as if it were spinning. And because of that, it's generating a field. So just its existence alone, and the fact that it has this quote-unquote spin, gives it a magnetic field, even without moving, even without orbiting. And so there are lots of things that have spin. And you can also think of spin as like mass and charge. Okay, they're all intrinsic properties, and different particles, different fundamental particles. Like if you ever look up like a particle physics table or something like that, they'll have, three quantities, three intrinsic properties: mass, charge, and spin. Some of them have full charge or full spin or whatever. Some of them have fractional charge, fractional spin. But various particles have different amounts. And it's not just electrons, right? Other particles, other fundamental particles, small particles like quarks and stuff, can all have spin. But yeah, that generates a magnetic field as well. And then you've also got just traditional current. Since this is just an intro physics class, this is the one that we're going to focus on. So this is just like flowing through a wire. The other stuff is inherently more complicated, and we're not really going to mess with that too much. Okay. So, so what we're looking at then, is basically when you have flowing charge and you're generating a magnetic field, this is what can create magnets. So how created, or how do they work? Right? Those pieces of rock that they discovered years ago in that country, and they're like, what the hell? How's that working? They weren't flowing charge through that, right? They weren't hooking it up to a battery and letting current flow through it. So how are they generating magnetic field, since a magnetic field requires moving charge? So in certain materials, or in every material really, those atoms that have spin and they're orbiting, they tend to align with atoms around them. And they start building up and they start generating a net magnetic field in a particular direction. And then sometimes there will be a break in it, like these lines indicate. And so all these things are going in different directions. And these areas with a particular type of direction are called domains. Basically you have these quote-unquote magnetic domains within a material. And how they work and how they align is determining what type of magnetic field you'll have. So you can imagine if they all aligned in one direction, you'd have a magnetic field, right? In that particular direction. But if they all maybe canceled out perfectly, you wouldn't have a magnetic field at all. And so this is what gives you different types of magnets. So types of magnets then is going to be determined by how the domains align. So you have a ferromagnetic material, and that is the strongest of the permanent magnets. And I say like permanent, you can lose a magnetic field over time, especially after interacting with other magnets. It basically changes how these guys align. But you have ferromagnetic, so that's the strongest of the magnetic materials. So this would be all domains align. Okay. You have ferrimagnetic, and this is some parts cancel. Okay, so you're starting to see some parts cancel out. So maybe you have one that's left, one that's right, you know, and some parts cancel out. And then you have anti-ferromagnetic, which the fields cancel completely. Okay, so all of them, you have an equal number of right and left, or up and down, or maybe, you know, you have diagonal canceling with another diagonal, and so on and so forth. Okay. Now, that's one way. So you can have permanent magnetic materials like those rocks. That's what those rocks were. They were some form of these. By the way, this isn't a just like a 1-0 scale, right? It's a sliding scale. So you can have a degree, right? So you're not completely ferromagnetic or whatever. So basically, unless you're ferromagnetic or anti-ferromagnetic, you are ferrimagnetic, right? You're some degree. You're like 98% ferro, which would be considered ferrimagnetic. Does that kind of make sense? So it's like a sliding scale. Now, there are two types of magnets which can be induced. So you can also induce fields. And maybe you messed around with this as a kid. You can actually hold a magnet to some materials, and if something wasn't magnetic before, it now is. And what you're doing there is you're aligning the magnetic domain yourself by putting an external field on it. So there's two here. There's paramagnetic, which produces a field that's attractive. I see my handwriting is top-notch today. You've got diamagnetic, which produces a field that's repulsive. And I should say attractive to the thing that caused it, the external magnet, and repulsive to the external magnet that caused it. Okay. All right. So going back, so far all we've done, looking at this, if we've defined magnetism, we said it was like a class of physical phenomena that's mediated by magnetic fields. We talked about how field lines look, and then we talked about what actually causes magnetism in the first place, which is moving charge. So now the next thing we want to figure out is what we always want to figure out in the first couple intro to physics, right? We want to know, and really all of physics, this is what you kind of strive for most of the time, is you want to know the effect that this has on other things. So we want to know the force. And so, to figure out the force, what we need to do is we need to figure out how field lines, what their actual direction is. Because if we know their direction, then maybe we can figure out what the force is on an object, okay? And so that's kind of like what most of this unit is about, is at first we'll figure out the direction of the field lines. And you can do that without any math. So we'll figure out how to do that. And then there's also the actual magnitude of the force. Okay, so we'll be able to figure out the magnitude of the magnetic force and its direction. And we'll also be able to calculate stuff like what the magnetic field strength is. Okay. So first of all, as I said before, so for figuring out direction, so we're going to basically ignore spin and orbiting. Okay. So if we have a wire, okay, so this guy's just like a wire, and we have a current and it's moving in this direction, the field lines will look like this. And at this point you're like, what are those weird symbols? I'll tell you. Okay. So let's start defining some stuff here. So I is out of the page, and X is into the page. So what actually happens with magnetic fields, and this is partially why they're so difficult, is these field lines circle around, they coil around like that. And so they go out and then go back in on the other side. That's what these symbols represent, is it's coming out, going in, coming out, going in as it goes around the wire. And it basically, it coils, the whole way down, okay? And so it'll come out around a wire moving to the right. It'll come out and then go back in. And how you actually discuss this is, if you want to talk about the field, use the word B. So the magnetic field is a vector, and it has this very specific direction, okay? A changing direction depending on where you're at in space. Kind of like the electric field did, okay? So it's a vector field. Okay. We use the symbol B to represent the magnetic field. And why wasn't M chosen? M actually is part of a different thing that you can talk about with magnetism, but that we kind of just reserve for later, higher levels of physics. B was another symbol or another letter not used, and so we just kind of went with that. Okay, so now, how do I know the direction? So how... Okay, so there's a couple ways. One, you can calculate it, and I'll kind of show you, well, no, I'm not really going to show you that, but I'll show you how to do it with the hand. So what you're going to use is known as the right hand rule, RHR. So this is the right hand rule. And there does exist a left hand rule, technically, but we're not going to do it. So this tells you the direction whoops, of conventional current. And remember what conventional current is. Conventional current is the flow of positive charge. So if we talk about the flow of an electron, we have to reverse what direction we get here. But anyway, what you do for this, there's two kinds. This is the first one. The thumb, so the right hand thumb is in the direction of current, and the fingers curl around the wire. So what I mean by that is, here's my right hand, okay? It's pointing in the direction of the current. And then these guys, the curl, that's the direction of the field. So on the far side of the wire for me, it's coming out, and then on the other side, it's coming in. So I recommend doing it yourself, getting used to it. But if you go back up and look at this, it's coming out, right? And I don't know how to do it on your screen, but it's coming out and then going in, okay? So try it yourself. Just literally match up your thumb to the page, to the video, okay? Match your thumb up, put it in the same direction, right, and then pull it out, and then see that it curls back in under. And basically the curl is the direction of the field. So the fingers, this is the direction of the field. Okay. So again, this is for conventional current. So if I were to do this and then I were to say, oh, we're actually looking at electrons moving, I would have to reverse it. So where it was in is now out, and where it was out is now in. Okay. So that's field lines number 1. I don't think, just trying to skip a lot of this. Let's see. Okay. I'm going to go ahead and do the other field lines now, the other right-hand rule. So this is the other right-hand rule. And this one's slightly more complicated. This is a situation where you're looking at a single charge moving in a field. So this is our positive charge, and the x's represent the B field. Okay. And we want to know what is the direction of the force. So what is the direction of the force on the positive charge? Okay, so how this right-hand rule works is V is the velocity of the charge. So this is the velocity. This is the direction of the velocity. And this is your index finger. Okay. Your the B field. So B, this is the magnetic field. And this is your middle finger. And then lastly, the force, or the direction of force, is your thumb. Okay? So, let's go ahead. I'm just going to do a really bad drawing of this. So this is your thumb. This is your index, this is V, your middle finger is B. And then you've got a couple other useless fingers there. 1, 2, 3, 4. Okay, and that's kind of how that looks. And these are separated. Dang it. 90 degrees. So you kind of like do this with them. Hold them at different angles. Okay. And then this, the force, is also 90 degrees. So it's basically perpendicular and it looks like this is how you hold them. Okay. Do it from a bunch of different angles so you can see. And the other two fingers are just kind of useless here. But this is the second form of the right-hand rule. So if we want the force on this thing, I go back up to the picture. I put my index finger in front, in the direction of V. Okay, so to the right. And then middle finger into the page. Okay, so this is going into the page. And now the direction that my thumb is pointing is the direction of the force, which is up. So it's pointing up. So the direction on the electron is up. So force I'm not going to say electron, positive charge is up. Okay? It's up because my thumb points up. So try it. Please work with this. Okay? And learn it. Okay. So now, let's go ahead. So we've learned direction. Okay? So, direction, check. What about magnitude of the magnetic force? Okay, so we've got a couple different scenarios here, right? So we learned the wire, and we learned this guy. So for a, let's look at the simplest case. So simplest case would be a charge, which isn't that simple, moving through a magnetic field, okay? And I'll list it and then I'll explain why it's true. So the force is a vector. Hoo boy, we got a lot here. Okay, so this is the force on the charge due to the field. Okay? This is the charge itself. This is the velocity of the charge. This is the magnetic field. And then this is known as a cross product. And I'll talk about what a cross product is in a second. Okay, so the force on the charge moving through a field. So this is the case where you have a positive charge moving. So kind of just like that one that we just did where we figured out direction. So this is a charge moving through a field. Oops. Kind of like this. So what is the force? What we got here is that the force on that charge is equal to the charge itself. So if the charge is, getting larger, then the force on that charge should increase too. Whoops. So the force on that charge should increase too. But you also have the velocity of the charge. Okay, so if it's moving faster, remember I said the flow of charge, the movement of charge is what generates a magnetic field. Because it's generating its own field by moving, if it moves faster, it should generate a larger force. And of course, if a magnetic field is larger, that will increase the force on the object. Okay, so if any of those increase, that increases the force. Now what about this cross product here? So if you remember from Physics 1, we used a cross product with torque, okay? And it was R cross F, right? And that was from Physics 1. And what I said back there when we were looking at it, right, what generates the most torque is if they're the most different, right? So if the radius and the force itself, if it's perpendicular to it, that generates quite a bit of torque. Well, the same is true here. So a cross product is something that is a measure of how different two vectors are direction-wise. So if they're perpendicular to each other, it's the most different they can be. And so what we're looking at is basically what this means is if the velocity is in the same direction as the magnetic field itself, there's no force at all. If they're perpendicular to each other, it's the most force that it can be. And so what you actually see then is this can simplify into magnitude QVB sine theta instead of having to do the cross product. Now, if you are in engineering physics or you're going to go on in math or something like that, at some point you'll have to learn how to do cross products. And in my notes online, I do show how to actually do that. But it's not super essential for this class. Discussed it, and I usually I do have like one type of cross product question, but for this semester I won't. I do think it's good to learn, but if you don't need it, you don't need it. So yeah, that's kind of where we're at. So this is it. This is the equation that you'll use. But what the calculation does, if you actually do the cross product, is it tells you the direction as well. It gives you both the magnitude and it gives you the direction without having to do the right-hand rule. But since we can use the right-hand rule to figure out direction, we don't really need to do the calculation, or we don't really need to do the cross product part. And we can figure out the magnitude from this equation. So this is a charge moving in a field. The other thing I mentioned this when talking about torque as well. The reason it's sine theta is when they're in the same direction, it's sine of 0 degrees, which is 0, which makes the force go to 0. And when it's perpendicular, gives you the most force because sine of 90 degrees is 1. Okay. So that's basically how that works. Okay. So now then, let's talk about a really quick case. So this is a case, this is a pretty interesting case, actually. If you get a charge moving in a uniform field, so here's the quick short case here. So the short, or a quick example here real quick. We'll do actual examples soon, but a quick example. So a charge moving in a uniform field. And most all of the fields that we'll be talking about are going to be uniform. You start introducing changing fields and it becomes really bad really quickly. But we're just going to do a uniform field. So what will actually happen is this guy ends up moving in a circle. Which is pretty interesting, actually. And you must be thinking, well, how the hell does it move in a circle? Okay, so here's our charge, and here's the direction of our charge. We're gonna do a, like this. So I hypothesize, I tell you, well, I don't hypothesize, I just tell you it's gonna end up moving in a circle. So why is that? Okay, so let's examine it like this. This is our direction. We use our right-hand rule. I forgot to do the X. And it looks like this. The direction of the force will be up. Okay, so force. So if force is up, it's going to start moving the charge that way, right? It will physically push it up. So now you get a case after it's in that area where it's like this. And you've still got the same thing. And so you do the same thing. You push in, you point up, right? So B is in, okay? The direction of the force now pointing to the other direction. And so now it points in that direction. And now you've got this scenario. And the same thing ends up happening where this guy will now curve down. So what you end up getting is that the force ends up just moving in a circle. So what you end up getting is this. Okay. And I think it's this way, so it's motion. And this is in a field like that. So it's actually pretty interesting that it does that. So if you want this, okay, so I said before that the force on this thing is QVB, right? But remember that it also equals MA from before. So this is Newton's second law, right? And this can still apply here. So if we want to map the motion of this thing, then what we can do is A becomes V squared over R because circular motion. And so what we get is QVB equals MV squared over R. The V's cancel, and you get this relationship. And this is for a, whoops, where am I in my life? Okay, and so this is for a circular charge A circular charge. What am I thinking? For a charge, moving in a uniform field. Q is the charge. B is the magnetic field. This is the mass of the charge. V is the velocity. R is the radius of the circular motion. And so you'll basically just get that the charge just keeps going in a circle, and you can actually get the velocity, and you can map all of that. The other thing you can do, we can get the period of rotation. So T equals 2 pi m over QB. This is the period, if you remember. And you can also get the frequency, which is, the frequency was 1 over the period, which is, so the frequency, how often? Doesn't do that. And this actually, real quick, is known as cyclotron. That's a special name, I guess. Frequency. Okay. All right. So that concludes the force on a single charge moving in a field. But now, what about the force on like a long wire? Okay. Drinking my coffee here. So force on a long wire. And I say long as in it's basically infinite length, because if you start cutting it off, it starts being difficult. So this equation that we derived earlier for a charge moving in a field basically turns into this. Where this is the current, and notice the current is considered a vector because it has a direction with it. This is the length. And again, it needs to be sufficiently long, which all of our stuff will. And this is the direction of field. Okay. So we do the same thing we did before, where we say, you know, we're not doing the cross product, and we get ILB sine theta, and this ends up turning into F equals ILB when perpendicular. So when I and B are perpendicular. Let me do that. Which most of the time they will be in here. Okay. So that's a wire in a field. Okay. Force of a wire in a field. You also can do force on dual parallel wires. Okay. So first off, for this, we need the magnetic field from a wire. So the B field from a wire is okay. I didn't really give you the B field from a charge because we're not really talking about it. We're not talking about the rotation or whatever, but we will talk about the B field from a wire. And we'll also use that for like other stuff like solenoids and things like that, which are just differently shaped wires. But we don't really do just a charge by itself too often, if you're curious. So we need the B field from a wire because we need that for the force on dual parallel wires. So the B field from a wire, this is the B field if you remember. Like if that was the wire, this was the B field, and this is the magnitude of the B field. So this is the magnitude of B field right here. Okay, so we start off, if you remember electrostatics at all, we always had that epsilon naught. For magnetic field, we have mu naught. And this is the permeability of free space, is what it's called. And it's basically how the magnetic field permeates through free space. And mu naught is always equal to 4 pi times 10 to the minus 7 Tesla per meter amp. So this is a Tesla, and it's the units of B fields. Okay. There's also a smaller unit, which is Gauss. Let me get that real quick. Can't believe I never talked about what that is, but I'll do it real quick. I think it's like 10 to the minus 4 Tesla or something. Hold on. Let me Google it real quick. Yeah, 1 Gauss equals 10 to the minus 4 Tesla, so okay. So, let me get back to where I was. What the heck? Okay. So that's mu naught. I is the current. Pi, it basically comes about because of the derivation for it. We're not really going to go for that, so we're not really going to talk about the derivation too much. But I is the current. R is the distance from the wire. One thing of note is it's not in R squared, so it doesn't fall off as 1 over R, or 1 over R squared. It falls off as 1 over R, which is a little bit different. Okay. So now remember, so we want the force, so we want the force on one wire due to another. So what we're looking at is this and this. So what's the force on this guy? Okay. So turns out what it is force equals ILB, right? Because this was the force on the wire in another field, but we're going to replace this with that equation. Okay, so force, so this is wire 1. Here, I'll go ahead and just define it, and then I will redraw it. So the force on 1 due to 2, on 1 by 2 equals I1, the length of 1, and then the magnetic field of 2. So it's the magnetic field of 2 that's interacting with 1. So this is I1, L1, and then you sub in that equation. where that's the difference between them. So this, oops, equals, I'm just going to go ahead, I'm not going to go through all this stuff, I'm just going to write it in its easiest form. Okay, which is this. Oh, jeez. This up. Okay. And this is basically the force I1, L1, and that's the distance between them. So it's the force on one wire, on wire 1 due to wire 2. Okay. So, that's basically it for this lecture. So let's do a real quick summary. Moving charges generate a B field, and a B field is a magnetic field. I would usually abbreviate this. So this is a magnetic field. You can have several moving charges, but we'll talk about mostly conventional current. I'm just going to leave it. And then with conventional current, we can get the force from a moving charge. So the force, so a moving charge, so forces, moving charge in a B field. So F equals QVB sine theta. Okay, I'm just going to do this. And then the force a wire of current experiences in a B field. And then the force on one wire due to another just redraw that. U naught, I1, I2, L1 over R, 2 pi. I think that's right. Let me just make sure. Yeah. And then this is the B fields we talked about. So those were the forces we talked about, and then the B fields, B field from a wire that we talked about. We didn't talk about any other example because it's inherently more complicated. Was this. So these were the magnitudes of the forces and the magnitude of the B field for directions. So those were directions, or those were magnitudes. For directions, use right hand rule. And there were two types. Force is thumb. BRI is index. And then B is the middle. The other one, thumb is the current. Curl is B fields. Oh, one last thing I forgot. For dual wires, forgot this. For dual wires, the direction is attractive. So the direction of force. Direction of force is attractive if same current direction and repulsive if opposite directions. All right, and that's pretty much it for the electromagnetism. In the next one, we'll do examples basically, and I'll show you guys how to navigate those. Okay, all right, thanks.